Okay, guys, so continuing with our discussion of electrochemical cells, we're going to talk about some non-standard cells. So let's just jump right in and talk about what a standard cell is and therefore what a non-standard cell is. So in a standard cell, we assume that the concentration in both the cathode half cell and the anode half cell is 1 molar. And there's a lot of reasons where that would not be the case. If a cell has been running for a certain amount of time, then we know that the concentration in the cathode cell is going to be decreased and the concentration in the anode cell is going to be increased. So both of those would have concentrations different from 1 molar. If for some reason the solutions were not made at 1 molar initially, so maybe something is limited in its solubility, or perhaps like silver is very often limited in its solubility, or materials weren't available. So if the solutions weren't, or there was an excess, we wanted it to last for longer, then our solutions might not have been made at 1 molar initially. We're also going to talk about something called a concentration cell, where the solutions are deliberately made at different concentrations in order to cause a voltage to flow where it might not otherwise. So when cells are not at standard conditions, the cell potential does not equal the standard cell potential. And we're back to that little not notation. So remember to pay attention to whether we have the not or not. Not or not. All right, so let's talk about non-standard cells. So the farther the change is, whether it's a change in concentration, well, that's kind of what it is, then the farther that change is from standard cell potential. And that's just common sense. The bigger the changes are, the greater the change from standard cell potential. And generally speaking, the farther our reaction is from equilibrium, the greater that magnitude of the cell potential is going to be. So of course, we like to be able to quantify this. So we're going to talk about the Nernst equation. So the Nernst equation allows us to calculate cell potential, when the two cells are not at standard conditions. They're not at 1 molar concentrations. So our Nernst equation is this. We have the E, the cell potential at the given conditions, is equal to the standard cell potential minus R, where R is our gas law constant, times the temperature in Kelvin, divided by the number of moles of electrons being transferred, times Faraday's constant, times the natural log of Q, where Q is our reaction quotient. So this should look fairly familiar. This looks a lot like some of the other equations that we've used in this unit. All right. When we're at equilibrium, our forward and reverse reactions occur at equal rates. So our battery is going to be dead. If the forward and reverse reaction are occurring at equal rates, then there's no overall electron transfer. We have a dead battery. And our cell potential is going to be 0. So that's one case where our cell is non-standard when we're at equilibrium. Okay, moving on to something that is actually useful, we're going to talk about something called a concentration cell. In a concentration cell, the anode and the cathode are made of the same material. So we have, in this particular case, a zinc anode and a zinc cathode. We have a zinc solution, zinc 2 solution. But the two solutions are at different concentrations. And we have some sort of a porous partition that allows the transfer of some ionic species, but not of the zinc. And when this happens, the electrons are going to flow. So we want to get these to the same concentration. That's going to be the driving force that causes this reaction to happen. And so in order for these two solutions to reach the same concentration, the one with the lower concentration needs to increase and the one with the higher concentration needs to decrease. And so the way that that's going to happen is for this to decrease, electrons would need to flow this way so that some of our zinc ions become solid zinc. our zinc ion concentration would decrease. At the same time, on the other side, if electrons are flowing this direction through the wire, then that means that our zinc is losing electrons, and therefore we are increasing the concentration of zinc ions on this side. So losing electrons, this is oxidation, this is our anode, and gaining electrons is reduction, this is our cathode. So the concentration is, the electrons are always going to flow from the lower concentration side to the higher concentration side. So we have zinc 2 becoming zinc 2, and we use this little notation of writing the molarity down here so that we can see. Now, standard cell potential here, well, the potential of the anode and the potential of the cathode are the exact same because they're the same material, they're the same electrode. So what does that mean that our standard delta E, our standard cell potential is? It's 0. So we're going to calculate our cell potential using our Nernst equation. We're going to assume we're at 25 degrees Celsius. And we have our E naught is going to be 0. Temperature is going to be 298 Kelvin. R is our gas law constant. N, how many electrons are being transferred? Well, we are going from zinc 2 to solid zinc, so that's 2 electrons. Faraday's constant and natural log of Q. Now remember, Q is the reaction quotient. So our Q is going to be the product side concentration over the reactant side concentration. So we're going to have 0.1 over 1. And so we can plug all of this into our Nernst equation, and we get that our cell potential is 0.030 volts. Now that's a pretty low voltage, but it is a voltage. And so we can actually use a concentration cell to cause a current flow. That's a lot of work. You don't actually need to be able to apply the Nernst equation quantitatively. You need to be able to apply the Nernst equation qualitatively. So what happens to voltage if we have a cell and it's at standard conditions and the concentration in the cathode half cell increases? That's the way I wrote the question. If that concentration increases in our cathode half cell, well, cathode half cell is our reduction side. So that is our product side. So we're going to have a higher number here, and that's going to decrease our cell potential. If it increases on the anode side, we're going to have a smaller number here, and that's going to increase our cell potential. So we need to be able to apply it qualitatively, not quantitatively. Okay, another common application of non-standard cells is after a cell has run for a little while. So when an electrochemical cell has run for a period of time, that means the concentration of the anode solution is going to increase and the concentration of the cathode solution will decrease. And that means that our cell potential is going to decrease. So, and we know this, as a battery gets used, it loses its potential. So that's it for non-standard cells. As always, if you have any questions, let me know.